Hello everybody. Today we are going to discuss electrochemistry, the new chapter. It's an introductory video. Myself, Dr. Digna Varghese. Electrochemistry, the production of electricity from energy released during the spontaneous chemical reactions and the use of electrical energy to bring about the non-spontaneous chemical transformation. So electrochemistry is the study of relationship between the electricity and chemical reactions. It is this branch of chemistry that deals with the interconversion of electrical energy into chemical energy or chemical energy into electrical energy. So it is the branch of chemistry that deals with the interconversion of electrical energy and chemical energy. Okay. In other words, it is the study of relationship between electricity and chemical reactions. Electrolytes. An electrolyte is a chemical substance that produces an electrically conducting solution when dissolved in a polar solvents like water. This includes most soluble salts, acids, and bases. For example, soluble salts like sodium chloride, potassium chloride, acids like hydrochloric acid, H2SO for sulfuric acid, nitric acid, HNO3, and bases like sodium hydroxide, potassium hydroxide. These are known as electrolytes. This substance, when dissolved in water, it is produces an electrically conducting solution. Electrolyte, when dissolved in a solvent, separates into cations and anions. Here you can see a representation of cell. The electrolyte is taken here. Here we are considering the electrolyte as HCl. The yellow part is H plus and rose part is Cl minus. So this is a HCl molecule. It when contact with water, it is dissociate into cations and anions. Cations are in yellow color, anions are in pink color. Okay. So HCl molecule when dissolved in water, it will breaks into cations and anions. If an electric potential is applied to an electrolyte solution, the cations of the solution are drawn to the negative charged electrode. Okay, the cations are drawn into the negative charged electrode. Here you can see if potential is applied here, then the electrolytes in the electrolyte, the cations move to the electrode in which more number of electrons or negatively charged electrodes. Okay, cations move towards negatively charged electrodes while anions move towards positively charged electrons where the electron is deficient here. Okay, so a substance thus dissociates into ions in solution acquires the capacity to conduct electricity. Okay, such substance is known as electrolytes. The movement of anions and cations in opposite directions within the solutions that amounts to a or that produces a current. Okay. Electrolyte solution is electrically neutral. We know the HCl molecules breaks into H plus and Cl minus. Equal number of cations and equal number of anions will produce. So the electrolyte solution is electrically neutral. Electrolyte solutions can also result from the dissolution of some biological molecules. Do you know that? DNA, polypeptides. Polypeptides means proteins and synthetic polymers. For example, polystyrene. Such molecules also when dissolved in a suitable solvent can produce electricity. Okay, they are charged molecules. So these types of biomolecules or synthetic macromolecules like polymers that are termed as polyelectrolytes. Okay, polyelectrolytes. Remember the term polyelectrolytes, which contain charged functional groups. Okay, electrochemistry mainly deals with the electrical properties of molten or aqueous systems of substances referred to as electrolytes. Okay, electrochemistry also deals with the interrelation between the chemical action and the electricity in such systems or electrolytic systems. Electrolytes are broadly classified into two types. One is strong electrolytes and the other one is weak electrolytes. What is a strong electrolyte? A strong electrolyte is an electrolyte which is completely ionized in aqueous solution, even at moderately high concentrations. So then, what is a weak electrolyte? Weak electrolytes are chemical substances which is not completely ionized in aqueous solution at moderately high concentration. Examples for strong electrolytes, that is strong acids like hydrochloric acid, nitric acid, sulfuric acid. Strong bases like sodium hydroxide, potassium hydroxide. And their salts like sodium chloride. Sodium chloride is a salt formed from HCl and NaOH. Okay. And potassium nitrate, that is formed by when nitric acid reacts with potassium hydroxide. So these are examples of strong electrolytes. Examples for weak electrolytes are weak bases like ammonium hydroxide, pyridine, weak acids like acetic acid, hydrocyanic acid, boric acid, hydrogen sulfide, etc. There are other terms that we know, non-electrolytes, the chemical substances which do not furnish ions for electrical conductions, which are called non-electrolytes. For example, urea, glucose, sucrose, which when dissolved in water that do not break into ions. So they do not conduct electricity. Okay. Conductors. We know a conductor is a substance that allows electric current to flow through it. Okay. There is another term in connection with the conductance, that is insulator. That is a substance that does not allow any electric current to flow through it. Okay. There is two types of conductors. One is ionic conductor or electrolytic conductor. Second one is metallic or electronic conductors. What is an ionic conductor? Ionic conductor is a substance that allows the passage of electricity their molten state or their aqueous solutions undergoing chemical decomposition at the same time. Okay. These are also known as electrolytes. So, these conductors are also known as electrolytic conductors. Here, flow of electricity is due to the flow of ions produced by the dissociation of the electrolytes. Here, appreciable movement of matter accompanying with the electrolytic conduction. Examples are acids, bases, salts. Okay. What about metallic or electronic conductors? Metallic conductors are the substances that allow the passage of electricity through them without undergoing any chemical change, because in which the flow of electricity is due to the flow of electron. So it is also known as electronic conductors. Here, appreciable movement of matter does not accompany the flow of electricity in these materials. Examples are metals, alloys, graphite, etc. The main difference between the ionic or metallic conductors are given here. First one is, what about the flow of electricity? In ionic conductor, we know the flow of electricity is by the flow of ions. What about in the case of metallic conductors? It is by the flow of electrons. Next difference is change of substance. What about the change of substance? Here we know when electrolyte dissolved in a suitable solvent, it will decompose into cations and anions. So here decomposition of substance takes place. But in the case of metallic conductors, there is no such decomposition or no change of substance occurs. What about the transfer of matter? Here, there is involves a transfer of matter. When a potential applied to the electrolyte solution, the cations move to respective electrode and anions move to respective electrodes. So there is involves a transfer of matter. But in the case of metallic or electronic conductors, there is no such transfer of matter occurs. What about the temperature increases in the system? For ionic conductors, we know the conduction is due to the flow of ions. Increasing the temperature in the electrolyte, that means the velocity of the ions also increases, that move faster. So the movement of ions faster means the electricity increases. That means conduction increases with increasing temperature. Okay. What about when the temperature increases for when the metallic conductors? In the case of metallic conductors, the conduction decreases. That means we know in metallic conductors the electricity by the flow of electrons. Okay. When increasing the temperature, that means the vibrational motion of the electrons also increases. As the vibrational motion increases, the electrons undergo random movement. Due to the random movement of electrons, it will undergo collisions. Due to the number of collisions increases, it cannot move faster. Okay, so the conduction decreases. So these are the difference between the ionic conductors and the metallic conductors. So, Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. Okay, that means I is equal to E by R. So Ohm's law is expressed mathematically in this way: I is equal to E by R. The current through a conductor between the 2 points is directly proportional to voltage. That is, I is proportional to E. Okay. Here R is the an constant of proportionality, that is the resistance. That one arrives at the usual mathematical equation that describes the relationship. Okay. So I is equal to E by R. I is the current strength in amperes and E is the potential difference in volts and R is the resistance of the conductor in ohms. So Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. Here The proportionality constant is replaced by the proportionality constant here, that is R, resistance. So I is equal to E by R. Conductance or electrical conductance. Conductance is defined as the potential for a substance to conduct electricity. Conductance is the measure of how easily the electrical current, that is the flow of charge, can pass through a material. So it is a measure of how easily the electrical current can pass through a material. In other words, conductance is the reciprocal of electrical resistance, that is represented by 1 by R. So conductance is given as G is equal to 1 by R, where G is the conductance, R is the resistance. So conductance is the reciprocal of resistance. Its unit is ohm inverse. Here 1 by R. Resistance unit is ohm. So unit of conductance is ohm inverse. In other words, Siemens. That is ohm inverse is also known as Siemens. Specific resistance or resistivity. The resistivity represents the resistance of the material which has specific dimensions. That is, the material has length 1 meter and its area of cross section is 1 square meter. Okay. The resistance of a conductor is directly proportional to its length. The resistance of a conductor is inversely proportional to its area of cross section. So R is proportional to L, R is inversely proportional to A. Therefore, the proportionality term is replaced here. R is equal to rho into L by A, where rho is the proportionality constant. Proportionality constant is also called resistivity or specific resistance. So, if L is equal to 1 meter, A is equal to 1 square meter, the resistance is equal to rho. From this resistivity we can calculate as rho is equal to R into A by L. Okay. If specific resistance is defined as the resistance in ohms of a conductor of unit meter length and unit area of cross section. So its unit of resistivity is ohm meter. Specific conductance or conductivity. Conductivity of any conductor is the reciprocal of specific resistance. Specific conductance is represented by the symbol K. So it is the reciprocal of specific resistance. We know specific resistance represented by rho. Here rho is equal to, we know rho is equal to R into A by L, where R is the resistance, A is the area of cross section of the conductor, L is the length of the conductor. We know specific conductance is the reciprocal of specific resistance. So, we can write 1 by rho is equal to 1 by R into L by A. Okay. That is 1 by rho is equal to 1 by R into 1 by A by L, that is L by A. Therefore, K is equal to G into L by A. We know G is the reciprocal of resistance, that is conductance. So, K is equal to G into L by A. Unit of conductance or specific conductance or conductivity is ohm inverse, meter inverse. or ohm inverse is also known as Siemens meter inverse. So the conductivity or specific conductance is defined as the conductance of a column of unit length and unit area of cross section. Okay. Conductivity or specific conductance of an electrolyte solution is defined as the conductance of a column of unit length and unit area of cross section. L is equal to 1, A is equal to 1. So the specific conductance is equal to conductance. Conductance or equivalent conductivity. The conductance of that volume of solution containing one equivalent of an electrolyte is known as equivalent conductivity. It is also defined as equivalent conductance of an electrolyte solution of a given concentration is defined as the conducting power of all the ions produced by 1 gram equivalent of the electrolyte in the solution. It is denoted by lambda. The equation for lambda is equal to K into V. If the volume of the solution containing 1 gram equivalent of the electrolyte is volume centimeter cube, that is lambda is equal to K into V, where K is the specific conductance of the solution, V is the volume of the solution containing 1 gram equivalent of the electrolyte. If N is the normality of the solution, then lambda is equal to K into 1000 divided by N, where N is the normality. That is concentration in gram equivalent per liter. Okay. Volume is replaced in terms of normality, that is concentration in gram equivalent per liter of the solution. Therefore, lambda is equal to K into 1000 by N. The units of lambda is equal to ohm inverse centimeter square equivalent inverse, that is Siemens centimeter square equivalent inverse. The gram equivalent means the amount of substance whose weight in grams is numerically equal to its equivalent weight. Once again I will tell you, the gram equivalent is the amount of substance whose weight in grams is numerically equal to its equivalent weight. So, N is the normality, therefore that is the concentration in gram equivalents per liter. So, it is known as equivalent conductance or equivalent conductivity. So, it is the conductance of that volume of the solution containing one equivalent of an electrolyte. Conductance. Nowadays, electrolytic conductance is more often described in terms of molar conductance. Molar conductance is described as the conductance of all the ions produced by 1 mole of an electrolyte present in a fixed volume of the solution. In other words, molar conductance of an electrolyte solution of a given concentration is defined as the conducting power of all the ions produced from 1 gram mole of the electrolyte solution. 1 gram mole is equal to molecular mass of the electrolyte. Okay, it is represented by lambda m, that is molar conductance. If the volume of the solution containing 1 gram mole of the electrolyte V is equal to lambda m is equal to K into V, where K is the specific conductance of the solution. Okay. If M is the molarity of the solution, molarity means concentration in moles per liter. Lambda M is equal to K into 1000 divided by M, where M is the molarity. The units of molar conductance is ohm inverse centimeter square mole inverse or Siemens centimeter square mole inverse. Okay. Relationship between equivalent conductance and molar conductance. For an electrolyte solution, lambda equivalent is related to lambda molar, that is, equivalent conductance is related to molar conductance as lambda equivalent is equivalent mass of the electrolyte divided by molecular mass of the electrolyte into lambda m, or lambda equivalence is equal to molarity of the solution divided by normality of the solution into lambda m. Conductivity cell. Conductivity is measured by using a conductivity cell to make a measurement of the electrical resistance. It is a specially prepared cell which are used in conductance measurements. These are called conductivity cells. A simple representation of a conductivity cell is given here. The cells are made up of Pyrex glass. The cells of the conductivity cells are made up of Pyrex glass. Pyrex glass is actually 80.6% silica, 12.6% boron oxide, 4.2% sodium oxide, 2.2% alumina, 0.1% calcium oxide, 0.1% chlorine, 0.05% magnesium oxide, 0.04% FeTO3. So, these conductivity cells are made of Pyrex glass, which is fitted with two platinum electrodes. Okay, these are the platinum electrodes, which is welded to platinum wires. Okay, platinum wires, platinum electrodes which are welded to platinum wires fused into the bottom of two thin glass tubes. Fused into the bottom of two thin glass tubes. These are the two thin glass tubes. Here in this, which tubes containing some mercury. Here some mercury is there for making contact to the circuit by means of copper wire. This is the copper wire which is in contact with the mercury here. To this platinum wire is fused to the glass tube which is also in contact with mercury. Okay, the glass tubes are usually fixed rigidly into an ebonite cover. Okay, this is the ebonite cover, and ebonite means the brand name for hardened vulcanized natural rubber. It contains 25 to 80% sulfur and linseed oil, so that the distance between here it is fixed by the ebonite cover, so that the distance between the electrodes remain constant. So this is a simple representation of a conductivity cell. Constant. Cell constant is defined as the ratio of the distance between the conductance titration electrodes to the area of electrodes. K is equal to G into L by A. That is, specific conductance is equal to conductance into cell constant. So, the specific conductance K of an electrolyte is given by conductance into cell constant. Cell constant is the factor with which the observed conductance of an electrolyte solution is to be multiplied in order to get this specific conductance. Okay. So for any given conductivity cell, the distance L between the two electrodes and the area of cross section of each are constant. Hence the quantity of L by A is constant, which is actually known as the cell constant. The unit of cell constant is centimeter inverse.